Hi guys, hope you're enjoying this to know. Today we're going to have our lesson on equilibrium. And as you recall, when we talked last week, chemical equilibrium is talking about the rates of the forward and reverse reactions. So we're talking about reversible reactions and those rates being equal. So whatever the rate of the forward reaction is, the reverse reaction is going to be equal to that. The concentrations of reactants and products at equilibrium do not change. They change as they're getting to equilibrium, but once they're at equilibrium, they don't change. So reversible reactions we show with a double arrow. So you can see I have the two ways that you might see it. You can use either of those ways to draw out your reactions. Either way is correct. But basically a reversible reaction is we have reactants and products forming, we have reactants forming products, and at the same time we have a conversion of products forming reactants. So that's what a reversible reaction is. Now I want to take a look at these graphs on this slide. So I want to take a look at the graph on the left. I wrote the balanced equation for this reversible reaction. The graph on the left is showing the forward reaction. The graph on the right is showing the reverse of what I have written. And you can notice that the SO2 and the O2 are both starting at higher concentrations because they're the reactants. SO3 is the product, so it's starting at 0. As the reaction proceeds, you can see on the y-axis we have time increasing as we go to the right. Concentration increasing on the y-axis up. So time on the x-axis increasing, and as it's increasing you're going to start to see SO3 more of it form. We're starting at 0 because when we start initially at this reaction there's no product in it, we only have reactants. So the reactants will decrease and the product will increase. Sorry, my writing on the screen isn't working very well. And then you'll notice that they all level out at equilibrium. So at equilibrium, that's when the concentration levels out. The same thing's occurring if I look at the reverse reaction. If I start with the reverse reaction, SO2 and O2 are not formed yet, but they will increase till they reach equilibrium. SO3 is my reactant in the reverse, and it will start to decrease as products start forming. And again, you can see they all level off at the same concentration as they do in the forward reaction. So the concentrations of each species may be different, but at equilibrium, the concentration of each species stays constant. So this is what that is showing you in these particular graphs. Now when we look at these equilibrium or reversible reactions, we're going to calculate constants for the reactants. The constant does not have units, but it's a ratio that's based on the products over reactants. And so you can see that I have a given reaction here, and this given reaction has lowercase a, uppercase a, lowercase b, uppercase, and so on and so forth. You can see there. So the lowercase letters stand for the coefficients, the uppercase letters stand for the reactant or product. When I write an equilibrium expression, I'm only going to use gas and aqueous states. So if there's anything that's a solid or liquid, it is not going to be put in the equilibrium expression, only gases and aqueous states. So we're assuming that everything's a gas in this given reaction because you can see that I have brackets around C and D, they're my products. The brackets mean concentration. The little exponents are my coefficients of C and D, so lowercase c and d. If they're 1, then you would put a 1 there. If they're 2, you would put a 2 there, so on and so forth. And then you can see in the denominator, I have the reactants. So I have products in the numerator and reactants in the denominator, to whatever power the coefficient is. So that's how we set up the equilibrium expression. And the K value when I solve for K, again, it doesn't have units. But if the K value is really large, greater than 1, then that means it favors product formation. If the K value is small, less than 1, then it favors the reactants in formation. So the K value tells us a little bit about the reversible reaction, or this equilibrium reaction that we're looking at. So on the screen I have a typical reversible reaction that you might see, and we're going to just write the equilibrium expression. I didn't give you any concentrations for anything. We're just going to write the expression based on this reaction. So in the numerator is where I'm going to put the concentrations of the products. So in the numerator I'll have the concentration of SnO2 to the first power because the coefficient is 1, and CO to the second power because the coefficient is 2. Both of them are gases, so I'm going to use both in the equilibrium expression. Now when I look on the reactant side, I have tin as a solid and I have carbon dioxide as a gas. So the only thing I will put in the denominator will be the concentration of the CO2 gas. I'm also going to put that to the second power because there's a coefficient of 2. So that would be the equilibrium expression for that particular reaction, and then we could solve and find the value of K, and that K value will tell us if products or reactants are favored in this expression. Now a couple things worth mentioning, and I mentioned them before. The brackets just mean that it stands for concentration, and concentrations are always in moles per liter at equilibrium. Exponents are the coefficients. I already mentioned that, so you have to make sure that your chemical equations are balanced correctly. And something really important, this last one, the KEQ changes with the temperature of the reaction. So anytime you write a K value, you're going to say at a specific temperature. The problem will always tell you what temperature the reaction was done at, because if I change the temperature, KEQ is going to change. So a scientist needs to know what temperature that reaction took place at, and they will record that in every data entry that they write. And just a quick review, the value of KEQ indicates whether products or reactants are favored. So if it's greater than 1, products are favored, less than 1, reactants are favored. We can also use the pressure of a gas, partial pressure of a gas, from a equilibrium equation to solve for K. So if everything in the reaction is gaseous, then we can use the partial pressures, and we would have to be given those partial pressures in atmospheres, and we would plug them in just the same as we would plug in the concentrations in moles per liters. So this is really showing you the same thing, except that I'm going to have the partial pressure of B, which is our product, to the lowercase b power. If there's a coefficient there, you would write that in, take it to that power. And then in the denominator, I would have the partial pressure of A in atmospheres to the lowercase a power, whatever that coefficient is. So it's set up exactly the same way, but everything has to be gaseous in the reaction, and you have to be given the partial pressures. So you can't do something that everything is gaseous with the if you're given concentrations, then you would be solving for KC, not KP. Okay, so KP just stands for equilibrium using the pressures. So we're going to look at the expressions for KC and KP only if KP is applicable. Remember, everything in the reaction has to be a gas in order for us to use KP. Okay, KEQ and KC I kind of use interchangeably, so I don't want that to confuse you. KP always means we're using pressure. Okay, so if we look at the first one and we want to write expressions for the first one, we would only be using the things that are aqueous or gaseous. We have 3 species that are aqueous and 1 that's a liquid, so we would not be using the liquid. Now I can't write a Kp for this one because there's nothing that's gaseous. Everything is aqueous. So for this one, I would be writing the Kc or Keq of F minus and the concentration of H3O plus, both to the first power because there's no coefficient, or the coefficient is 1, over HF because the coefficient is 1 there as well. And again, no Kp. For the next one, you can see I could do both for this one because everything is gas. So if I was given concentrations, I would be solving for Kc. So Kc is for concentrations, and I would be writing the brackets. So I would have NO2 to the second power because there's a coefficient of 2, and then I would write NO squared in the bottom, and then O2, like so. I could do the same thing for Kp if I were given the partial pressures of each of the gases. It would be set up the same way. I would just use parentheses because it's not really a concentration. So I would have NO2 squared, and then I would have NO squared and O2 gas, like so. Now I want you to pause the video and I want you to try the third one. Can you write a Kc and a Kp based on that reaction? And I will come back on in a minute to show you the answer. And as you can see, I cannot write Kp because there's no gaseous substances in this reaction. However, I have aqueous, so I can write Kc. I would not use water because water is a liquid. Anybody who's in biochem might notice that this reaction is an esterification reaction. I'm reacting a carboxylic acid with an alcohol, and I'm forming an ester and water. So if you were in biochem or you're in biochem now, that reaction might look familiar because we're actually doing those reactions right now with esters. Now the last thing that I want to do with you is talk to you about the K value of the Haber process. And the Haber process is the formation of ammonia. So let me write that formula or that reaction down for you. So here's that reaction. Now we're going to look at some of the information. Sorry about that, I'm on the right slide now. I had the wrong slide up there. Right formula, but wrong slide. Okay, so I have the reaction at the bottom, the Haber process, formation of ammonia, N2 gas, reacting with 3 moles of H2 gas, forming 2 moles of ammonia gas. So we can look at a reaction and we can manipulate the K value for a reaction based on if we're going in the forward or going in the reverse, or maybe we change the coefficients for some reason. And so we're going to look at some manipulation of the K value today. And this is the last thing I'm going to cover, and then I'm going to give you your homework and you'll be good to go. So let's look at A. A says to calculate the value of K at 127 degrees C. There's that temperature. These concentrations were determined at that temperature. Okay, so you can see that I have the concentrations up here. All I'm going to do is plug and chug. So I'm going to set up the problem and I'm going to plug it in my calculator and get an answer. So as you can see on the screen, I have worked out the problem and I wrote out the Kc products over reactants with the proper coefficients and solved the problem putting in the proper concentrations, and plug and chug is what I say, and you end up with 3.8 times 10 to the 4th, and this is a pretty big number, much greater than 1, so products are going to be favored in this reaction. Now you can see letter B says calculate the value of the equilibrium constant at the same temperature, but notice the reaction is reversed. If the reaction is reversed, then KEQ is going to look like this. So there you can see that KEQ or KC, it's just reversed. Now I have ammonia in as a reactant on the denominator, and in the numerator I have the now products because we're in the reverse. So basically, this is just taking the reciprocal. So I can take the K value that I already calculated and do 1 over K. And that's going to give me the new K value for the reaction in reverse. So I plugged in 3.8 times 10 to the fourth, which was our K value for the forward reaction. Writing this as the opposite reaction, I'm going to get a K value of 2.6 times 10 to the negative fifth, which makes sense. If the products are favored in the forward reaction, the reverse reaction isn't going to be favored as much, so I have a lower K value less than 1, much less than 1, 10 to the negative fifth. So K is really, really small. And in letter C, it says calculate the value of K at 127 degrees C for the reaction given by this equation. And you can see in this reaction that all of the coefficients were divided by 2. So the 1 that was originally in front of N2 is now 1/2. The 3 that was originally in front of hydrogen gas is now 3/2. And 2 divided by 2 gives me 1 for the ammonia, so I have a coefficient of 1 there. So everything was divided by 2. If you see coefficients divided by a common factor, the corresponding root is taken. So for this example, we divided by 2, so we're going to take the square root of K to get the new K value. If the coefficients were divided by 3, then we would take the cubed root of K. So here you can see I took the square root of our original K value, 3.8 times 10 to the fourth, and the square root of that is 1.9 times 10 to the second. One other thing I want to mention is if we multiply by a factor, so we multiply the coefficients by a common factor, then we would raise K to that power. So if I multiplied through by 2, I would raise the K value to the second power. If I multiplied by 3 all the way through, then I would raise K to the third power. So dividing, I take the root, the corresponding root of K. Multiplying, I raise K to that power. Now for homework, there's an equilibrium expression worksheet on the class page. You are going to do numbers 1 through 6 and 13 through 15. It's all the problems on the left-hand side of the worksheet, and submit that into the Dropbox. You're also going to work on page 549 in your textbook, number 27, 29, and 31, and that also will go into the Dropbox. Things have just recently changed as I'm doing this video, so stay updated with the task sheet. Since we actually have a snow day tomorrow, things are all going to kind of get pushed back. So just follow the task sheet and things on the class page so that you know where we're going this week. Hope you enjoyed that video, hope it was helpful, and hope to see you soon in class.